Good. So we got a final coming up next week?
Yeah, we have one on Wednesday.
Okay. We're going to have 2 hours before then. So
yeah,
do you have your review material?
Yeah, so, and I've got like the most important subjects that I really want to go over outlined.
Let's do it. Can you verbalize it?
Yep, for sure.
Okay.
So the first one is just to simplify each, and it's like the identities.
Okay.
So this one is tan squared of x minus tan squared of x sine squared of x.
Anything else?
No, that's it.
Okay, so we're simplifying that. Whenever you see an expression that has the same thing in both terms, what should you think
of? Sine and cosine?
Factoring.
Oh, factoring. Okay.
Factoring. I see a tan squared there, and I see a tan squared there. I'm thinking that if I factor that tan squared out, I'm going to get somewhere.
Tan squared.
Notice what I have left.
Oh, I see. Okay, that equals 1 minus.
Squared.
Yeah. So that becomes tan squared x cosine squared.
Exactly.
Oh, I see how this is going to work. I think.
That becomes sine over cosine, sine squared over cosine squared. Final result
is just sine squared.
Exactly.
Cool. Okay.
Always think factoring, whether you're in trig or algebra or calculus. Always be thinking factoring.
Okay. The next one is secant squared of x minus 1 over sine squared of x. And that's it.
Just like that?
Yep.
Well, the first thing I'm inclined to do is put secant in terms of cosine.
I was thinking that too, but is there an identity that has secant squared of x minus 1?
No, there might be, but I don't think so. The identity is tan squared of x plus 1 equals secant squared of x. Ah, you actually hit on it.
So that can become tan squared of x?
Exactly.
Okay.
Tan squared of x is sine squared over cosine squared all over sine squared. What's that become?
That becomes cosine squared. Or 1 over cosine squared, so secant squared of x.
Right.
Okay.
Which is kind of amazing. Some of these trig identities are really shocking. Well, that one's not like I thought it was. But some of them truly are. They're just not, there's no ballpark that you can use as to whether it's even close, to a proper answer.
Yeah.
Make sure that each step you're making a proper identity.
Oh, yeah, that's true. The next one is 1 over 1 plus cosecant of x plus 1 over 1 minus cosecant of x.
What do you suppose the first step would be?
So maybe multiply each side by the conjugate.
Don't even need to do that. Notice that if we tried to find a least common denominator, what would it be?
1 plus cosecant
times 1 minus. In other words, you can always get a common denominator by multiplying the two denominators. That won't always give you the least common denominator, but who cares? We get a common denominator every time if we multiply the two denominators.
Okay.
Now, what goes up here on the left? Top left.
On the top left, it becomes 1 minus cosecant of x.
Notice the advantage of writing it like that, instead of multiplying it together.
Okay, I see how that works, yeah.
Because it makes it really, really easy to see, have we changed it? And no, we haven't. It's exactly what we started with, and that's what we want. Is we want to make sure we do not change this fraction. What goes in the upper right?
1 plus cosecant x.
Now, we can operate on the numerator. And let's go ahead and multiply the denominators together, because this might turn into a nice trig identity. What do the numerators do?
It just becomes 2, doesn't it? Because
Yep.
Yeah, okay.
Now, let's look for a trig identity for 1 minus cosecant squared.
That can be cotangent squared.
Well, let's see. I don't know what it is, but...
Because cosecant squared minus cotangent squared equals 1. So cosecant, I may be wrong there.
Now, hold on. This is the identity, correct?
Yes.
Solve that for 1 minus cosecant squared.
It becomes negative cotangent squared of x.
So I can cross that out and put negative cotangent squared of x, and then simplify that one more step so we don't have stuff in a denominator.
It becomes negative 2 tangent.
Negative 2 tangent squared.
Okay.
See how I get there?
Yeah. Okay. So the next one is to verify.
Okay.
And it is secant squared of x minus 1 over secant squared of x.
Equals?
Equals sine squared of x, sorry.
Only because you said it was a verifying problem.
Yeah.
Okay. Well, that looks like a trig identity. That I can put in terms of cosine. In other words, once I use the trig identity on this, it's going to go to some kind of tangent squared, either plus or minus. And when I use the identity on this, it's going to go to cosine squared.
Yeah.
That's going to go to sine over cosine squared. That's definitely the path we want to take.
Okay, I see. Yeah.
So you kind of have to be able to think a few steps in advance. So first of all, what does secant squared x minus 1 equal to?
Tan squared of x.
What's secant squared x in the denominator equal to if I put it in the numerator?
Cosine squared of x.
Now use the quotient identity for tangents. That cancels with that. So the key here is when you see expressions like that, think Pythagorean identities.
Okay.
And then that turns it into tangent, which can be expressed in terms of sine and cosine. So can secant be expressed in terms of cosine. So all of that's going to come down and simplify quite easily.
Okay, I see how that works.
Yeah. You just kind of got to get used to what to look for when you see an expression. If I see this expression, I'm not looking for any identity. I'm looking to multiply that by the conjugate. But if I see that expression, I know that's sine squared x.
Yeah.
In other words, whenever you see 1 plus minus a trig function squared, think your Pythagorean identities. Always.
Okay. Okay.
What else?
The next one is 1 over 1 minus sine of x plus 1 over 1 plus sine of x equals 2 secant squared of x.
Now, normally, the moment you gave me that, I'm thinking I'm going to multiply by the conjugate. Top and bottom. But when you add it to a fraction that has its conjugate in it, I don't need to do that. If I just add these two fractions, I'm going to get the right thing. What's the common denominator between these two fractions?
1 minus sine of x, 1 plus sine of x.
Now, what's the numerator in the top left?
1 plus sine of x.
And in the top right?
1 minus sine of x.
What's the top become?
2.
What's the bottom become?
The bottom becomes...
Always look for that's difference of perfect squares factored.
Just 1 minus sine of x squared.
Which converts to?
Which converts to 2 secant squared x. Oh, cool.
Exactly. First of it converts to that. And then that converts to secant squared in the numerator. You get that.
Okay. Okay, cool. The next one is cotangent squared of x.
Automatically thinking Pythagorean identity. Go ahead.
Over 1 plus cosecant of x is equal to 1 minus sine of x.
That's it?
Over sine of x.
Alright, let's see. That would be cosecant minus 1. If you don't know what to do, as a last resort, convert everything to sines and cosines. Well, I can convert that easily to sines and cosines.
Yeah.
Since that is the reciprocal of sine, I can convert that to sines. And then once we get everything in terms of sines and cosines, it'll be easy to go from there.
Okay.
So that's what I'm going to suggest. I could convert this to cosecant first, but I don't really see where that, well, hold on a second. That would be cosecant squared minus 1. This is 1 plus cosecant squared. In other words, here, there's always multiple ways to go on these verifying. In other words, let's examine a couple steps. that would be, excuse me, that would be cosecant squared minus 1 in the numerator, correct?
Yes.
And then the denominator, I got that. Now the numerator becomes cosecant minus 1 times cosecant plus 1. Well, the 1's cancel. That cancels. That's what I'm left with.
Okay.
Now, can we turn it into this on the right side? In other words, that's relatively straightforward. Well, cosecant is 1 over sine minus 1. Get a common denominator. It's sine. It's 1 minus sine x.
Oh. Huh.
Bingo. This is a little bit like name that tune. If you can name it in 2 notes as opposed to 3 notes, you're doing a little better. So I got to think we probably verified that as easily as we could possibly do it.
Yeah.
There are other ways to do it. Maybe the same number of steps, maybe 1 or 2 more. You're still going to get to verify it.
Mm-hmm.
But I guess the clue here is the fact that we started out and there were all these signs over here.
Yeah.
Okay, and this cosecant is the reciprocal of sine. So in a way, we started the problem out with 3 sines. In other words, we had 1 plus 1 over sine. Well, when you got that many signs in a problem, just convert that somehow to sines or cosines. I could have actually done that. I could have converted that to cosine over sine.
Yeah.
But I think that would have been a little longer. I think that would have taken a few more steps.
Mm-hmm.
Which tells me that when you see cotangent squared, use the Pythagorean identity immediately.
Okay.
Okay?
Okay.
All right.
Cool. The next one is it wants to find all the solutions of the equation on an interval of 0 to 2 pi.
Okay.
So the equation is sine of x plus root 2 equals negative sine of x.
What's the first step?
I am unsure.
Get all your variables on one side of the equation, get everything else on the other.
Oh, okay. I think I remember how to do this now. Huh.
Yeah, solving these it's really algebraic. It's algebra. It's really no different than solving a polynomial. If I had x plus root 2 equals minus x, how would you solve that? You would add x to the left, you'd move the root 2 to the right.
Mm-hmm.
That's what we do here.
Yeah. So it becomes 2 sine of x equals negative root 2.
Now what?
And then if you divide by 2, it becomes sine of x equals, root 2 over 2. Negative root 2 over 2.
Yeah, and where does that occur? Where's the first place that occurs?
3 pi over 4.
Sign is positive in the second quadrant.
No, so it's 5 pi over 4.
Good. And the other place is in the fourth quadrant?
7 pi over 4.
There's your 2 answers.
Okay. Huh. Cool. Okay, the next one is 3 tangent squared of x minus 1 equals 0.
Okay. First step?
The first step is to move the 1 over, so it becomes 3 tan squared of x equals 1, and then you divide by 3, so it becomes tan squared of x equals 1 over 3. Okay. Tan
Going, because the next step is not that. The next step is ripe for error.
And then if you square root both sides, doesn't it become 1 over root 3?
It's plus or minus 1 over root.
Oh, plus or minus 1 over root 3.
That makes a huge difference. That's going to give you 2 more answers.
Yeah.
Whereas if it was strictly plus 1 over root 3, it'd be first and third quadrant. But if it's plus or minus, it's going to be first, second, third, or fourth quadrant. So what are these angles we're talking about? When you see that, you know it's in all 4 quadrants.
Isn't the first one pi over 3? And then the second one is...
I think it's pi over 6. I think it's 30.
Or is it pi over 6?
Now let's draw our 30/60. That's 1, root 3, 2. The sine of 30, or excuse me, the tangent of 30 is 1 over root 3.
Oh, yeah. Okay.
Almost better to not rationalize that. In fact, I'm finding all kinds of students where it's better to not rationalize. It's not only okay to not rationalize. I know your teacher has told you that, hasn't he?
Yeah.
But it's actually better to not rationalize. Okay, what's the second quadrant angle where that's the same?
5 pi over 6.
And the third?
And then it's 7 pi over 6, and then it's 11 pi over 6.
There's your 4 answers. Now, if you miss the plus or minus, you'd have missed half these answers. I don't know how much you lost, but I suspect half the number of points. So, I don't know how to help students remember this. The only thing I constantly repeat, and it doesn't seem to help, is that when you solve an equation by taking the square root of both sides, always begin your answer with the words plus or minus. Always. Never will your answer not begin with plus or minus.
Yeah.
When you are solving an equation by taking the square root of both sides, like that, then always start your answer with those words, plus or minus. I wish there was a song.
Yeah.
I know they teach you a song for the quadratic formula, but I never heard anybody teach a song for that, and yet that's probably the most common error that I see of all my students. Even the ones that are going to get in the 99th percentile, like yourself probably, they make that mistake.
Okay.
Okay?
Okay.
All right, what else?
The next one is cotangent of x times cosine squared of x equals 2 cotangent of x.
Notice what would happen if we made the mistake of dividing both sides by cotangent x. We get cosine squared x equals 2. Then cosine x would be square root of 2, and we could solve for that. But you can't do that. And the reason you can't do that, whether it's an algebraic equation or a trig equation, is you can never divide both sides of the equation by a variable that might end up being 0. Because if 0 is one of the answers, you're going to lose it. Always. You lose it 100% of the time. So that's not the way to solve this. The way to solve it is to subtract this from both sides. So I end up with much like a quadratic, get 0 on one side. And the reason I want 0 on one side is that I know I can take a greatest common factor out of that, and I'm going to have the product of two things. Well, when you get the product of two things equals 0, you can solve it. If I get the sum of two things equals 0, I can't do a lot with it unless there's something common in there. And in this case, there is. What can we factor out?
The cotangent?
Now, we got this times that equals 0. So either cotangent x equals 0 or cosine squared of x equals 2. Where is cotangent x equal to 0? Is the domain the same on all of these? Is it 0 to 2 pi?
Yeah.
Okay, where does that occur?
No, that's the on the interval.
Where is cotangent of x equal to 0? In the unit.
Cotangent of x equal to 0 at pi over 2.
Good.
And 3 pi over 2.
Good. Where's cosine squared of x equal to 2? First of all, solve that for cosine x.
Okay. So cosine x equals root 2. Plus or minus root 2.
Where does that occur? We know it's going to be all four quadrants.
So all the pi's over 4.
Once we see that plus or minus,
it's all the pi's over 4s.
I don't think it is.
Is it not?
No, I don't think so. That's 1 over root 2.
Isn't? Oh, no, never mind.
Are you supposed to solve these without a calculator, or does it say?
It doesn't say.
Because the other way I can draw this triangle is root 2, and 2. And that makes things a little easier. Now we're wondering where the cosine of x is root 2 over 1. Well, let's take a different approach. Can the cosine of x be root 2?
I'm unsure.
Here's what the cosine curve looks like. Goes between 1 minus 1. There's no place on that entire domain where the cosine of x is equal to root 2, which is approximately 1.41.
Okay.
So this is impossible. Can't
So
be.
you'd write no solution?
No, I've got a solution up here. I still have a few solutions. My
Okay.
solutions were pi over 2 and 3 pi over 2. So I still have two solutions.
Oh, okay. So
But
you'd
this
only
one,
write those.
that one is not possible. Cosine squared can never be equal to 2. Always remember that. The sine and cosine can never be greater than 1 or less than minus 1. And secant and cosecant are always greater than 1 or less than minus 1. They're never in the middle range. If somebody tells you the secant of x equals 1/2, that's impossible.
Mm-hmm.
Just like
Okay.
cosine could not be root 2. It threw me for a minute because I didn't think of it like that. I was trying to draw a triangle where we could come up with a solution. But the very first thing you always want to look for is to make sure that it's not outside its domain. The domain of x, when I'm talking about a function cosine of x, the domain is minus 1 to 1. That's it.
Okay. Okay. Okay.
And that's okay, incidentally. In other words, the fundamental rule of algebra says that if you have one thing multiplied by another thing and it's equal to 0, one of those things has to be 0. It does not say both of them have to be 0. So that's where extraneous solutions come from, is that it's what's only required here is that one of these two things that I have circled is equal to 0. Well, we were able to make cotangent x equal to 0, and we were not able to make that equal to 0. That's fine. It doesn't have to both be 0. And whenever you come up with extraneous solutions, that's really the mathematical principle underlying it, is that only one of them has to be 0.
Okay. Okay. Well, the next one is 2 sine squared of x minus sine of x minus 1 equals 0.
When you look at this, what do you see?
I see a quadratic.
Exactly. Factor it as if it were a polynomial.
Okay, so it becomes 2 sine of x and sine of x. And then they both have to be 1, and you just have to figure out where the plus minus goes. It would be...
Favor the middle term.
Yeah. It would be
That means
minus on the right.
minus there. By
Yeah, minus on the right side.
middle term, I mean I produce a minus 2 sine of x there, and I need to be more heavy on the minus than the plus.
Yeah.
That's what I meant by favoring the middle term. And that's your answer. Now, go from there.
Sine of x is equal to 1 at pi over 2 and 3 pi over 2.
I think it's equal to minus 1 at 3 pi over 2.
Oh, minus 1, sorry. I think it's just pi.
There's only one place where it's equal to 1.
Yeah, it's just pi over 2.
When you're taking inverse trig functions of the number 1, it's the only number where sometimes there's only one answer in the unit circle. Every other angle or number is going to give you 2 quadrant answers. But if you look at the sine curve, notice that there's only one spot where it's equal to 1. That's right there.
Okay.
Okay, whereas any other angle you want to talk about, If I said, where is it equal to 1/2? Well, that's there and there. Where is it equal to minus 1/2? That's there and there. In other words, most everything is going to give you two answers except the number 1.
Yeah. Okay.
Okay, and then what else has to be true?
Sine of x is equal to 1/2 at...
Negative 1/2.
Oh, negative 1/2. I'm sorry. Okay, yeah. Negative 1/2 is equal to that at 7 pi over 6.
Well, you're good at this. I've never
And
met
11
anybody
over
that
6.
thought in radians so well as you do.
Thank you. It's our teacher kind of just drilled it into us a little bit more than degrees.
No, it helps, I think. In other words, I have some students that spend the entire semester converting radians to degrees and then back to radians if they have to have the answer in radians, which is a big pain. Far better if you can think in radians. And you do very well, think in radians.
Thank you.
So, those are your 3 answers.
Okay. Okay. The next one is 2 sine squared of x plus 3 cosine of x minus 3 equals 0.
Ooh. What are we going to do to this? First of all, notice that it's very difficult to solve a trig equation if you have 2 different trig functions.
Yeah.
Especially if one of them is squared. So, your first thought should be, can I turn everything into either sine or cosine?
You could convert sine squared to 1 minus cosine squared.
Let's do it. Now we have a quadratic in cosine x. Now we just have to solve that quadratic. So first in, let's distribute.
You're
not going to make it easy for us.
I know.
Let's see. If we divide everything by -1, I get 2 cosine squared x minus 3 cosine x plus 1. Okay. Because that would turn negative, that would turn positive, yeah. Okay. Now, all we got to do is factor that.
Minus 1, that becomes 2 cosine of x and cosine of x, and it's 1 and 1, and isn't it just both negative?
Yeah, it's both negative and there's only 1 and 1, so either that works or we got to resort to the quadratic.
Yeah.
And it's not beyond them to put one in here that you would have to use the quadratic to solve. But this one actually works.
Yeah.
It's my answers. Starting from left to right.
Cosine x equals positive 1/2.
Occurs.
It occurs at cosine x pi over 3, and no, 5 pi over 3.
And the second one, cosine x equals 1, where? Again, look for only one solution.
It's just pi.
No?
It's just 0, sorry. Or is it, would you just put 2 pi instead of 0?
No, it's just 0. And the reason is that when they restrict the domain, they write it like this.
Okay.
In other words, 2 pi is not part of the domain.
Okay.
At least that's the way I've always seen it. I have never seen a less than or equal to there.
Yeah,
Because they
no.
don't want you having to put two answers that are the same. In other words, 0 and 2 pi are the same angle.
Yeah.
So they only want you to go from one to the other, but not including both.
Mm-hmm.
So again, there's only one answer for the bottom one, but we have 3 solutions. So what you can kind of see here is factor, factor, factor. That's always what you want to be doing. If you can't factor it, then convert and then factor. But when you see a quadratic or something that looks like a quadratic, try to get everything to the same trig function and treat it as a quadratic.
Yeah. Okay. Okay. Cool. Well, the next one wants us to find the exact angle for each using the sum and difference identities.
Okay.
And the angle is cosine of 75 degrees.
Now there are multiple ways of doing this. You could come up with 75 by saying 45 and 30. You could come up with 75 by saying 120 minus 45. And either of those answers, in other words, let's just talk about that for a second. That's going to work because I know what these are. That's going to work because I know what each of those is. In other words, when I use the sum and difference, I get cosine of 1, sine of 1, plus or minus the reverse. And I know what sines and cosines of all of these angles are. But this is the preferable method because they're both first quadrant. So we know all trig functions are positive in the first quadrant. So this is the one I would choose. But like I said, there's literally an infinite number that you can choose. So first of all, let's start out with, tell me what the general A plus or minus B is.
A plus minus B.
Do they
okay.
give you a cheat sheet of any kind, Nick?
Yeah, they allow us one note card.
Okay. There's probably one that you want on there.
Yeah, definitely. Cosine A plus or minus B equals cosine A and times cosine B. And opposite, or so minus plus, sine A and sine B.
Okay, let's plug it in.
Okay, so it becomes...
Plug this in. So what's cosine of 30?
Cosine of 30. It is the x movement root 3 over 2.
It's cosine of 45.
Root 2 over 2.
What's the sine of 30?
1/2.
What's the sine of 45?
The sine of 45 is root 2 over 2.
So what we have is root 6 over 4 plus root 2 over 4. Believe it or not, this is a very common answer. You wouldn't think so, but it is. Root 6 plus root 2 all over 4. And that's what the cosine of 75 degrees is. In other words, we didn't need a calculator. We actually were able to figure out the cosine of a non-standard angle, in other words, one that was not multiples of 30 or 45, without a calculator.
Oh, I see. Okay, I see how that works.
Now, we were able to break that number up into the sum of angles that we know,
Mm-hmm.
That's always the key. Could also use the double angle. In other words, the cosine of 75 is also equal to the cosine of 150 divided by 2. And then I would have worked off 150.
Uh-huh.
So
Okay.
some of these angles that are not part of the unit circle that they forced you to memorize can still be figured out using sum and difference and double and half angles.
Yeah. Okay. Okay. Well, the next one is sine of pi over 2.
That's it?
Yep.
What is it?
Sorry, pi over 12, not pi over 2. I read that wrong.
I was going to say, that doesn't
Huh.
sound right. Okay,
Yeah.
so how can we state pi over 12 as a sum and difference?
We could do...
This is one you may not know instantly. I happen to know it just because I do it so often. But
Is it just pi over 6 and pi over 6? That's the only thing I can think of. Or...
that would be 2 pi over 6.
Well, yeah. That wouldn't work.
Here's what works.
Adding radians is always hard.
It is hard. You could do it in degrees. There would be nothing wrong to converting that to 15 degrees. And then once you convert it to 15 degrees, then it's 60 minus 45, right?
Yeah.
Okay. Well, in radians, when you take radians or not, 1/3 minus 1/4 is 1/12. I've done that so many times I have it memorized.
Okay.
Okay, so that's what we're looking at is 1/12, so we got to get 1/3 minus 1/4. Now, what is the general for sine sum and difference?
It is sine A times cosine B plus minus cosine A and sine B. I remember that one pretty well.
Yeah. No, I think there's a reason that they teach everybody the cosine one first. And they do.
Yeah.
It's a bit odd, isn't it, that they teach the cosine one first? And
Yeah.
the reason is that the cosine one is cosine, cosine, opposite, sine, sine.
Mm-hmm.
You can figure out everything else. And once you memorize that, you know that there's 2 cosines and 2 sines in the answer. And so when you go to memorize the sine sum or difference, you know that there's 2 sines and 2 cosines and they're not together. So one is sine cosine, the other is sine cosine. We have to reverse the letters. So once you memorize the cosine one, I believe the sine one is easier to memorize. Because for one thing, that's the same. You memorize that is the same. And you don't have sine or cosine together like you do with cosine. With cosine, you have cosine, cosine, minus or plus sine, sine. But as long as you remember that the sine one has the sine next to cosine, you can't get it wrong, really.
Yeah.
So, what's this become?
It becomes root 3 over 2.
Let's
Oh,
well,
sorry.
just to add the step, minus, and I always put the sine first. In other words, I like keeping that first and first. You reversed them, which is fine. The property allows you to do that.
Okay, I see, yeah.
In terms of memorizing it, I find it easier to memorize if I keep the sine as the first term. And then sine of pi over 3 is
root 3 over 2
cosine of pi over 4.
is root 2 over 2.
Notice we're going to have a root 6 again.
from this one becomes 1, or that becomes root 2 over 2. But the last one, isn't that one cosine of A?
Ah, yes, sorry. That's cosine of pi over 3, so that's 1/2.
Mm-hmm.
So we end up with root 6 over 4 minus root 2 over 4. There's
That becomes,
6 minus root 2 again.
yeah.
Can't tell you how many times I see that root 6 in an answer.
Mm-hmm.
And it all has to do with these angles that can be expressed as sum and difference of our common angles.
Yeah, I see. Uh-huh. The next one is the last one actually, to use a half angle formula to determine the exact values of sine, cosine, tangent of the angle.
Okay.
And so this one is 15 degrees, and that is it.
We'll do sine,
Okay.
which is the same. Even though it's the half angle they want you to use, you have to double that. So you always have to go kind of the other way.
Okay.
Right?
Yeah.
And the sine of theta over 2 equals what? You want this on your cheat sheet.
Yeah. I don't know if I remember
Obviously.
this. I don't know if I remember this formula at all. I got it.
It's either, pretty sure it's this.
It's 1 minus cosine, yeah. 1 minus cosine of theta over 2.
The cosine of theta over 2 is similarly looking, only it's 1 plus cosine theta over 2.
Mm-hmm.
So I believe those are you looking at a book? Can you verify those?
Yeah, I just did. I looked at my notes.
Good. So the only one we need is the top one. And notice the only thing we need is the cosine of 30 degrees. In other words, when they say theta, that's theta, 30.
Mm-hmm.
I'm taking the sine of theta over 2. So my theta is 30 degrees.
Okay.
Okay? Which means it's the square root of 1 minus cosine of 30 degrees.
Cosine of 30 degrees is root 3 over 2.
And you just have to worry about the algebra. And the way I do these is always do the numerator first. Apply it. So you end up with the square root of 2 minus root 3 over 4. And I can take that 4 out. You see how?
Yeah, with the 2.
Well, with the 1/2.
Or the 1/2, sorry.
4 out. It's that.
Mm-hmm.
So, in other words, these two are the same. So that is the sine of 15 degrees. And notice how strange this answer is. We have a radical inside a radical.
Yeah. Okay.
And it would be incorrect to not take that 1/2 out. You would not want to leave an answer like that, because that's the square root of 2 minus root 3 all over the square root of 4, and the square root of 4 is a whole number. So when you can take a whole number outside of a radical sign, always do it.
Okay.
Now this answer I could put in a variety of ways. That's probably the most straightforward. Same thing. Yeah, you don't get too many math problems where you get radicals inside radicals.
Yeah.
Actually,
No.
that was one of the foundations of math was this might surprise you, but they were able to do quadratics for thousands of years. But solving cubics and quartics was a whole nother story. And as you have found, it's very difficult to solve cubics and quartics. And the only method known was the radical method, where you produced answers that were radicals inside of radicals. And I don't even know that method, but I've read it in the history books, that that's the only way they used to be able to solve quartics and cubics, and fifth degree equations and sixth degree equations and stuff. But you always ended up with answers that were radicals inside radicals, similar to this.
I see. Cool. Well, that was actually my last problem.
Okay, perfect timing.
Yeah.
Nick, I will talk to you on Tuesday, I believe, or Monday?
Yeah, Tuesday.
Tuesday at 7, I think?
Yeah.
Talk to you then.
Awesome. Talk to you then. Thank you.
Bye-bye.